Hello everyone. Once again, it's my pleasure to welcome you all to MSP lecture series on interpretive spectroscopy. In my last lecture, I was discussing about importance of IR spectroscopy in metal carbonyls, and also when we have different type of mixed ligand complexes having one or more carbonyl groups, it also gives, especially the stretching frequency of carbon monoxide, gives vital information about the electron density surrounding the metal ion, and also the donor and acceptor properties of other ligands as well. The donor and acceptor properties of other ligands present along with CO in a metal complex have remarkable influence on the stretching frequency of CO. So let us continue some more examples about IR spectra of metal complexes, and also let us try to learn more about force constant and its relationship with frequency. So here I have given a list of carbonyls, homoleptic carbonyl complexes, neutral complexes, anionic complexes, and also cationic complexes, and also I have given the stretching frequency for CO in centimeter minus 1. And some of those things I already discussed in my previous lecture. If you see here, nickel tetracarbonyl, it shows around 20-60 centimeter minus 1, whereas cobalt tetracarbonyl anion, of course, when it is dimeric, it is neutral because it is a 17 electron species, and now with COCO4 minus, it is an 18 electron species. Here stretching frequency is 1890, drops considerably because of excess of negative charge on cobalt. So if more and more electron density is there on metal, they will become better pi donors. As a result, what happens? The stretching frequency of CO drops considerably because of population of electrons into pi star or antibonding orbitals of carbon monoxide. And similarly, if you see here, we have dianionic compound here, iron compound. For example, Na2FeCO4, if you consider, stretching frequency even further drops to 1790 here because two negative charges are there. And then when we look into positively charged metal ions such as MnCO6 plus, here metal is a reluctant pi donor because of negative charge. As a result, not much significant change is there in the stretching frequency of carbon monoxide, and it is towards higher side. That means CO bond is more stable and MC bond is relatively longer. And of course, CrCO6 we have substantial amount of back bonding because of D6 electronic configuration and also metal in zero valence state. And again, vanadium hexacarbonyl anion is more or less comparable to that of COCO4 minus, and free carbon monoxide is around 2143, and some books say 2130 and all those things, but to be precise, it should be 2147 centimeter minus 1. And then the effect of binding can be clearly seen here. In terminal binding of a carbon monoxide to metal, the range is around 1850 to 2120. When it acts as a bridging ligand holding two metal centers, it drops considerably to 1750 to 1850, and when it is bridging three or more metal centers, so stretching frequency even further drops, and here when it is bridging three metal centers, it comes around 1620 to 1730 centimeter minus 1. That means more and more bridging would leads to almost carbon monoxide behaving like ketonic carbon monoxide group we come across in organic chemistry. Influence of the trans ligand can be clearly seen in this series of complexes I have shown of MOCO3. MOCO3 moiety remains intact throughout, and other three carbon monoxides are replaced by different type of phosphorus compounds and also nitrogen donors, and also diene is there and also pyridine is there. When you see again, the same trends are observed here. Here it is not about anionic or cationic charge present on the metal center, it is about the pi acceptor ability of ligands. And if you see here, the pi acceptor ability of ligands are considerably dropping when you go from PF3 to pyridine, and of course PCl3, and we have trimethyl phosphide, triphenyl phosphine. About these things already we analyzed it in my previous lecture. And astronitrile, it's only sigma donor. Diene also, partly it can take into pi star, but it's a poor pi acceptor, and pyridine. And in all those things you can see how consistently the CO stretching frequency is dropping, because when few or more carbon monoxides are left and others are only sigma donor, the maintenance of electron or minimizing the electron repulsion by taking back bonding falls only on 3 carbon monoxide groups. As a result, what happens? Stretching frequency drops considerably here. And also how immensely this data helps in arriving at different positions of these ligands in spectrochemical series can be seen here. And of course, when we talk about the position of ligands in a spectrochemical series, we are considering both sigma donor ability, pi donor ability, as well as pi acceptor abilities. Considering all those things, we have made spectrochemical series. Similarly, for back bonding ligands also, one can have spectrochemical series in this order, and this follows this order here. So now let us look into some problems here. This is related to stretching frequencies of different groups. For example, here 2 metal complexes are given of thiocyanide complexes of mercury as well as iron, with mercury is in +2 state and also iron is in +3 state. And also corresponding stretching frequencies are given here, 2120 and 710 centimeter minus 1 in case of mercury complex, and in case of iron complex the values are 2055 and 1828. For assigning the linkage here, whether S is connected to mercury or N is connected to mercury and also iron, we have to have some information about free SCN. So free SCN stretching frequency is given here. The C triple bond N stretching frequency is 2053, and also for CS it is 748 centimeter minus 1. Just for your information, I have also given isocyanide. In this one, C triple bond N resonates around 2060 centimeter minus 1, and also it can have ranges depending upon what kind of R groups we have. It can have anywhere between 2060 to 2260 to 2240 centimeter minus 1. Now the question is, in this complex, which is the donor site? And if you go back to linkage isomerism, whether S is coordinated to mercury or N is coordinated to mercury, and same thing is true in case of iron, whether S or N. Now let us compare the data here with the data we obtained for these mercury and cyanide complexes. If you see, because the wave number of Cn for the complex is higher, so this is higher compared to this one for SCN, and the wave number for CS is lower in the complex compared to free CS. Because of this one, we can conclude that S is coordinating to mercury. This is analogy. And let us look into iron complex. In case of iron complex, if you compare the stretching frequency of Cn with that of that one, this is much lower here. On the other hand, CS stretching frequency is much larger compared to free ligand. That indicates probably in case of iron, N is coordinating to FP3 center. From coordination chemistry point of view, let us say I do not have data for comparison for the free ligands. Then how to assign? Simply by looking into it. Yes, we can see here two things about look into soft and hard interactions. Mercury 2+ is a soft center. So since it is a soft center, it would prefer to have a soft donor atom, and hence S is a soft donor atom. So probably you can think that mercury is connected to sulfur. On the other hand, iron 3+ is hard center. It would prefer a hard site. That means probably nitrogen is going from. In this way also you can analyze and you can arrive at the right answer. And also if you see mercury ore is cinnabar, mercury sulfide, so that also tells that mercury has more affinity towards S from that point of. But here, without any ambiguity, simply by comparing the data with the data for free ligand, the stretching frequencies, we should be able to tell the correct linkage of such ligands which are capable of showing linkage isomerism, whether S is coordinating, S is binding or N is binding. Let us look into another example here. This is a octahedral complex of cobalt, pentacyanothiocyanato-cobaltate. It can appear, of course, because of linkage isomerism, it can appear in two isomeric forms, which give rise to the following IR absorption bands. So here we have 26, 2065 and 810, and another one is 2010 and 700 centimeter minus 1. So by simply comparing to whatever the discussion I had with respect to mercury and iron complexes I showed in my previous slide, you should be able to judge that yes, in case of isomer 1, N is binding, whereas in case of 2, S is binding, you can say without any problem. And of course, you can also write the corresponding isomers having octahedral geometry without any problem. I am not going to write those things. Probably you can write and examine those things. Let us look into another example here. The following infrared absorption bands are observed for the complex containing a bipyridine ligand and also thiocyanide ligand. It is NCS, not NSC. In the region of NCS stretching modes, that is, we have a total of 4 stretching frequencies are there: 2117, 295, 842 and 700. Now that means it's probably a mixture of 2 isomers are there, and we should be able to identify stretching frequencies corresponding to N coordination to palladium and also S coordination to palladium. Again, with our previous experience of interpreting data in case of mercury 2 compound and iron 3 compound, we can conclude here that when we have 20, 95 and 842, this can be assigned to palladium having NCS bond, and similarly when we look into the data 2117 and 700, this can be assigned to palladium having SCN type of linkages. So this is how we can interpret, and we can say without any ambiguity how the linkage of NCS takes place, and then how we can interpret and elucidate the structures by giving the right kind of stretching frequencies to N as well as S bound complexes. So now another problem is, it's not a problem, it's just for analysis. You are already familiar, I have spoken many times about CO stretching frequencies. CO stretching vibrations of CO can be found at 2155 centimeter minus 1. That's the free carbon monoxide shows at 2150. Again, here it's at a different region. That's what I'm telling you. So books, from books to books, this value varies, 2130 to 2160, it goes up to that one. But nevertheless, the stretching frequency of free CO is always greater than what we see in case of metal carbonyls, unless there is no back bonding at all in those metal complexes, but lies in the range of 2100 to 1800 in metal carbonyl compounds. That's very much true. The chemical bond in metal carbonyl compounds is a superposition of a sigma metal to carbon bond and a metal to carbon back donation. So that you are already familiar, I have showed you examples, and also I have showed you bonding modes through orbital interactions. What information is obtained by the mean value of CO stretching modes according to the part of both contributions to the chemical bond in the following charged metal carbonyl ions. That means whether we can look into the sigma donor component and pi acceptor component, whether we can separate these two entities based on comparing the data for a series of compounds, keeping the metal constant and changing the number of carbon monoxides, or going for cationic, anionic and neutral, and also replacing some of the carbon monoxide in a metal complex with sigma donor, pi acceptor, sigma donor, pi donor, and also sigma donor and pi acceptor type of ligands. And then we can analyze, and probably we can, but still the separation of sigma donor and pi acceptor abilities or components is very difficult, because often we see they complement each other, but nevertheless it gives some idea about the exact position of some of these ligands in the spectrochemical series. So now let us look into the values given for a series of compounds here: NaCO4 2094, COCO4 minus 1946, FeCO4 2 minus. So here we can conclude very nicely that when we go from early metals to late metals, despite having enormous electron richness, they are reluctant pi donors. That can be seen in case of whether nickel tetracarbonyl or palladium or even silver complex having carbon monoxide, whose stretching frequencies are much higher. But on the other hand, early metals, despite having electron deficiency and having less than 6 electrons, they act as excellent pi donors, and positive charge makes them reluctant pi donors, but negative charge on metal makes them better pi donors. And as a consequence of this one, what happens? The influence is on metal to carbon as well as carbon to oxygen bonds. As more and more back bonding comes here, not in this direction, comes in this way, what would happen is this bond become more and more elongated and stretching frequency drops considerably. So this information already we have discussed in n number of times. Let us move on to other problems. Now a very interesting problem is there. Let me read it out. An absorption at 3650 centimeter minus 1 in the IR spectrum of a compound, say X, has been assigned to an OH stretching mode. To what wave number is this band expected to shift upon deuteration? That means a complex is there, we have a OH stretching frequency is there, and if we replace H with D, what would happen to the stretching frequency? That is the question. And also during this one, certain assumption has to be made. What assumption one has to make while doing this calculation to find out approximate stretching frequency or absorption band for a compound having OD instead of OH group. So now from the standard expression that you already know, nu bar equals 1 over 2 pi c into square root of f over mu, where f is a force constant, stretching force constant, and mu is the reduced mass. And that means basically we can consider here this nu is inversely proportional to square root of mu reduced mass. That means this is equal to, we can say, stretching frequency, or the frequency, absorption frequency for nu bar is inversely proportional to OH bond reduced mass. So in that case, what happens, assuming both the OD and OH have very similar stretching force constant, we can arrive at this equation here. If you write for this one, nu OD or nu OH equals nu OH square root of mu OH over mu OD. So now we know this relationship, and now we know these entities we can calculate, and we know this one. Now we have to calculate what is this. So now what we will do is reduced mass we have to find out in this fashion, and this is one way of doing it, or simply we can do this way also, Mn M2 by M1 plus M2. This would be rather easier. But if we do with the first one, what we have to do is, here oxygen is there, oxygen atomic weight is 16 and H is 1 and then D is 2, we should remember this one. So 1 by 16 plus 1 by 1, this is equal to 1.0625, and then this is for 1 by mu of OH. So mu OH equals, what we get is 0.9412 atomic mass units we are getting. And similarly we can also calculate now mu OD, this is equal 1 by 16 plus 1 by 2. So for this one we get 0.5625. If we go for mu OD, it comes around 1.7778. This you can do calculation. Now we put here the values. So this value is already given here, 3650, into if you put here values, this comes around 0.72757. So this gives approximately 2656 centimeter minus 1. So that means if we replace H with D, then the stretching frequency of OD drops considerably from 3650 to 2656 centimeter minus 1. So here the assumption is very important. In most of such problems where we come across replacement of one isotope with another one, probably we should assume that the stretching force constant would be very similar. Then only we can arrive at this kind of relationship here, and hence we can calculate the values and solve the problem. So let's look into one more example here. An absorption band at 3337 centimeter minus 1 in the vibration spectrum of NH3 shift to X value in ND3, find out the value of X. So again here we should come up with the same relationship whatever we saw. We know now, so this is inversely proportional to square root of mu. If we use here, So now let us calculate mu NH first. Of course, N we are considering 14, H1 and D2 for calculating reduced mass, and here also we can do directly or something like this also we can do it. It's 1 over 14 plus 1 by 1. So, this is equal to 15 by 14. So, this value will be 1.0714 and mu NH will be similarly. So, here this value is going to be 0.933 and here the value will be 0.5714. So, ND equals 1.7500. So, now we have to apply here. This is given here. So, that means the value of x is this one. So, this is how you can solve these very interesting problems. Let me come up with more examples in my next lecture. Until then, enjoy these problems. Thank you.